The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to today's webinar on thermal comfort simulation. We're gonna do some nice flow simulations today in the realm of architecture, engineering, and construction. Here's a little preview already on that slide. A few technical notes before we dive into the details of this session. We're using GoToWebinar today to stream this webinar, and I'll record it. So afterwards, in case you've missed a particular session or a specific part, or you want to listen to a part again, you will be able to do so. I think the recording should be up within the next 24 hours. Another technical note, the audio should now work. So there's this little feature where you can raise your hand. And if some of the attendees could quickly raise their hand to indicate that the audio is working well on your end, then I know that my setup here works and you can hear me clearly. That seems to be the case. Thank you very much. A last technical comment, the GoToWebinar application also allows you to ask questions. So at any point during the session, you can just type in the question you might have, and after the 20 minutes webinar today, I'll try to cover some of them. Experience shows that it's mostly more than we can cover, but there's also the SimScale forum, and my email address is also in the details of this webinar description, so feel free to reach out to me directly. All right, without further ado, let's move on. A few words of a motivation. Why is design for thermal comfort so hard, right? We're seeing lots of interest and lots of customers in the realm of thermal comfort on SimScale lately. And the main reason, and so I came to the conclusion that this is a very interesting field for a number of reasons. I think the design and engineering work in that field is particularly challenging, right? And I think it comes from the fact that the importance that thermal comfort or design for thermal comfort gets lately is only rising, right? The workforce needs to be more productive, people need to be more efficient, and so more and more employers, but also operators of commercial facilities think that thermal comfort is a decisive factor in the design of buildings, or particularly HVAC systems. So on the one hand, we want to be able to, condition the air exactly and being able to react to all sorts of external temperatures, yada, yada, yada. But on the other hand, we have the additional challenge that the emission standards as well as the energy efficiency standards become ever more restrictive, right? So here's a little chart on the right showing that heating, ventilation, and cooling of air is a big portion of the energy consumption of commercial buildings, right? And that's also true for other buildings. So we as designers and engineers of these HVAC systems are facing the challenge that on the one hand, we want to make sure that the occupants in the rooms we're designing are feeling comfortable at any point during the year, at any external conditions, but at the same time, that should be very energy efficient, and the HVAC system should be very sensible and sustainable. So that makes that thing particularly challenging. And so what we're going to do today is exactly work through such a scenario. The idea today is taking a look at a hands-on example where flow simulation can help to make better design decisions during the design of HVAC systems. Here on the left, you can see a typical application we're seeing on SimScale. That's a theater space, maybe a cinema, maybe some large-scale theater, where we can see on the left all of these occupants, right? So the humans are simplified to simple cubes. On the right, we can see the stage and a bunch of details, curtains, these sorts of things. And what we want to do today is do the conceptual design of an HVAC system that conditions that space, that ventilates this space. The challenges we're facing is that we've got tons of people in there, right? And all of them produce heat. That's the main factor we're going to look at today. We're oftentimes these design scenarios also involve, particular external temperatures, either a winter scenario, summer scenario. We're paying particular attention today to the heat produced by the audience, by the occupants in here. And there's it's interesting, there's many different thermal comfort models, right, out there being used, many different metrics engineers look at. Today, we're just going to look at two. So we're going to take a closer look at the ASHRAE 55 standard, as well as the effective draft temperature criterion, to sort of assess or quantify whether or not the audience in here will feel comfortable given our HVAC system. The first, let's say, we as engineers, we're getting this task, and so the challenge is now, or the initial task is, okay, design an HVAC system. So how are you going to do that, right? And so our initial sort of naive approach is sort of saying, okay, let's do the following. Let's bring in the fresh air from the two top inlets you can see here at the top, right? And let's position our outlets, so the return registers, below the audience. So under each seat, there's now a little inlet and a little outlet where the air leaves the room, and at the stage as well, right? You can see already it's sort of a simplified model, right? I think there's many HVAC engineers and designers among you, so I'm sure you immediately ask yourself the question, okay, why don't we bring in a diffuser here at the top, right? So obviously that air probably is going to be diffused rather poorly, but it's really this 20 minutes demo is really just, to get a sense for how SimScale is being used, how CFD in general can help in such scenarios. So back to the case, we're bringing in fresh air from the top. We're getting it out below the seats as well as at the stage. And obviously our humans produce a certain amount of wattage metabolic heat. And the two scenarios, here you can see already a little preview of the results we're going to look at in a second. The scenarios and the two models that we're going to use to assess whether or not our HVAC system deals well or is well designed with respect to thermal comfort. The first thing is the first model we're going to use is effective draft temperature, right? A metric or a model that is relative to the temperature, right? So it only looks at temperature differences as well as the local airstream velocity, without going into the details here. But later on, we're going to look at, so what we want is that the effective draft temperature is in the range of -3 and up to +2 Fahrenheit, right? That's sort of the range where people feel comfortable. Another model we're going to take a look at is the one proposed in ASHRAE 55. And here you can see a little overview chart. And later on, we're going to see the audience, the entire model being colored in these colors. We can see that the x-axis has the operative temperature, right, in the room. And then at the left, we've got airspeed, or on the y-axis, we've got airspeed in meters per second and feet per minute. And we can see that, and just a little overview here, we can see that at very low temperatures, it really comes down to the temperature in the room, right? So below 20 degrees Celsius, people feel cold, and at some point it gets comfortable, and then at some point it gets too hot, right? As soon as our velocity around the occupants gets higher than 0.2, around that area, people feel it's too drafty, right? And that again highlights this challenge we face when designing HVAC systems for thermal comfort, because we need to move air, right? We want to ventilate the space. We might be forced to bring in, cold conditioned air, warm conditioned air, heated air, these sorts of things. And so it's really a challenge to condition the room as we want it to be conditioned, while meeting everywhere in the room where occupants are these thermal comfort criteria. And we will see that this yellow versus green will be a challenge later, but more on that in a second. That's just a super, a very high level overview over this, because there's other factors at play, such as radiant temperatures, such as the installation, so what clothes are the occupants wearing, etc. For today's sessions, we're not looking at these things. Also humidity, right? And in today's sessions, we're not going to look at the details of that, but rather, get a rough overview of how this works and how customers on SimScale are simulating such HVAC systems to check for ASHRAE 55 compliance. So not going too much into the details, just getting an idea what this color scale means. Just 2 minutes on why SimScale, because lots of you might have already seen flow simulations for HVAC system design, right? And ultimately SimScale is, like you also can do flow simulations in there, so nothing new about that. The new things about SimScale is three core differences. The first thing, it's a web application, right? So it's accessible from any device, from anywhere. You just need an internet connection. Zero software, zero hardware footprint, which makes it very convenient, particularly in the AEC industry, because you might not be needing simulation all day long every week, right? But from time to time, depending on the project. Second, cost efficiency, due to the fact that you're renting both the software and the hardware. It's really an on-demand pricing model, right? So the initial financial commitment is very low compared to the rest of the industry, and you can just pay as you go the computing power you need. Last but not least, SimScale sort of is not just a software, but also a large community, and then we call it a platform where people collaborate with each other. Since it's web-based, people can just, with one click, share a project with our support, share a project with a colleague, or share a project with your client, and then you can seamlessly collaborate on such projects, and makes it easier to dig into that. That's going to be the setup. We're gonna maybe a few words to manage expectations. We're not gonna do an in-depth, walk through the software today and look at all features and how exactly you can set up such an analysis. There's other webinars and we've got a documentation. There's a SimScale Academy where you can learn how to do that. Today, it's really about how HVAC designers, engineers, how sustainability engineers use SimScale to design HVAC systems for thermal comfort. So just to get an idea how all of this works. These are actual screenshots from the platform. So you can see on the left, we're bringing in a CAD model. We've got many different formats you can bring into, and then you generate a mesh and set up the simulation, and then afterwards you're doing visualization of the results. And that's also going to be the main part of today's webinar. So we're going to discuss the results, how you can interpret them, and how it helps you in your engineering work. Today it's an internal ventilation simulation. But beyond that, and you can see on the left here two such analysis, right? On the top left, it's a cabin analysis. On the lower left, it's also a similar application for another customer. And then here on the right, you can see that you can also do external wind flow analysis. So this is one about pedestrian comfort, right, around buildings, which is also required, or where there's also quite some regulatory compliance necessary. And then here in the lower right, a contaminant control simulation. So that's a parking lot where we're looking at carbon monoxide distribution. Beyond that, it's not just a CFD tool. There's also structural mechanics and other types of analysis in there. So it's really a fully fledged simulation tool, completely browser-based. All right, demo time. Enough talking. Let's get our let's take a look at the software. Again, quick recap. That's what we're going to simulate on the left, right? The first scenario, the first HVAC system is top inlets, outlets at the bottom, stage outlets, and then the occupants as heat sources. So let's quickly, I'll bring in, let's quickly leave the presentation. And here you can see, this is the SimScale website, right? So that's a Google Chrome browser. So you just go to simscale.com and then you can log in. I'm already logged in, create an account here, and I see here the different analysis types, right, that I can run. I already prepared this project before, right? So let's take a look. And this is now the completed project, right? I just want to give you a feeling for how the software looks and feels. This is the initial design I propose, right? All right, let's hide a bunch of faces here to better view that. So you can see we've got the two large faces here at the top. We've got all the occupants with the small registers back, so where we're gonna bring the air out. And then we've got some additional outlets in front of the stage, right? Over here, over there, over there. And that's really going to be the, that's basically the whole preparation of the CAD model. Obviously, I haven't modeled each human, with a ton of detail, because it's simply not going to affect the flow too much. So yeah, and then just to get a feeling for how then the simulation setup looks like. So this is now a mesh, right? So I generated a mesh. Let's quickly bring it in so you can see that this CAD model has been divided in many small cells here, right? And all of this is again visualized in my browser. And that's, I think something like 12 million cells, something like that. So, no, 20 million cells. So we're talking about 22 million cells. So this has a complexity you could not simulate anymore on a normal, workstation or something. That's gonna need significant computing power, right? Also here, let's hide it here. So we can see that, all details have been resolved. So this looks good. Let's quickly hide the mesh again. And then just a feeling for the physics we set up. Let's take a look at the boundary condition, right? So we're talking about the outlets over here. Let's hide that a bit. So these are the outlets, right? As discussed, you can see them highlighted in blue. And these are the inlets highlighted in blue. And then we've got the sidewalls modeled with a fixed temperature. And then the occupants as a heat source, right? Heat flux on the occupants. And then last but not least, a couple of adiabatic walls. That's about it, right? And then afterwards, we can give this a spin and run it. And let's take a look. So this ran roughly for 12 hours, right? We ran that on a 96 core machine. So quite some computing power. We're going to see later what some analysis, how much computing consumption this was. But I think the beauty of again, this being a web application running completely in the cloud is that you do not have to have this computing power locally. So you can run models of complexity and of size that you could not do on a local computer. All right. So much, as a quick idea of how SimScale looks and feels. Let's go back to the presentation and see what the results of this analysis are. And in the meantime, I quickly check on if there's any urgent questions. But it doesn't look like that. All right, then let's continue. All right, the first design. Inlets at the top, outlets at the bottom, right? This is what we can see here is the velocity in meters per second plotted as a sort of as three different cut sections, right? One cut section going through the audience, two cut sections beyond or beneath the two inlets. And we can immediately see that the big red portion here means that we're bringing in all of this air, right? So they really have these heavy air curtains coming from the top, directly hitting the audience. So strong draft there to be expected, which you can see here on the right. It's poorly distributed, right? So I said that already earlier. So one troubleshooting could certainly be a diffuser. And then we've got all sorts of things happening here, right? Here there's some flows at the side that we don't really like, right? Where the velocity goes up. So overall, I mean, that doesn't seem to be too smart, right? Obviously, the temperature here plotted in Kelvin. So the red piece is 22 degrees Celsius. And also here, right, we're bringing in conditioned air, so cooler air, and it's being heated with the audience. You can see that the audience leaves or emits heat. And while around the inlets, we've got a decent cooling happening here at the top. We've got lots of heat being or a higher temperature, at the bottom a very low temperature. So again, it sort of confirms that our concern that this might not be the smartest ventilation strategy. And then now, talking about thermal comfort, this is effective draft temperature, right? And so we want this to be between 2 and -3. And so green is good, blue is not good, right? Blue is too much draft. Red is also not good. And we can see also not well distributed. So you can really now count the number of occupants that are not within or that are not in a seat that feels comfortable, right? According to EDT. And yeah, I mean, we did the counting, it's 15, right? So 15 of the seats are in an EDT range that is supposed to be not comfortable. Last but not least, ASHRAE 55. Here we can see basically in yellow what's not good, and in green what's good, right? Good is comfortable. Yellow is okay from a temperature perspective, but it's too drafty, right? So, and that's again, that confirms our picture we had before. All right, bottom line here is this is not, I mean, having the bringing in the air from the top directly over or above the occupant region seems not to be the smartest choice. We've got then these guys being too cold or not feeling comfortable around. We've got a lot of temperature or heat being heated up. And then a possible solution would obviously be the one we already discussed, right? Diffuse the inlet air better. But what we're going to do is we're going to change, or we're going to go for another approach. What we're going to do is the last two things here, right? What we'll do is we'll move the inlets to the side, and then we're going to switch the ventilation approach, right? We're going more for a not a displacement ventilation, but we'll bring in the air, the conditioned air from the bottom, not from the top. So if you will, more of a displacement ventilation approach and not a mixing ventilation approach. But that's not the piece here. It's just a different approach here. Okay, and you can see that here in the new design, right, where we compare design 2 with design 1. On the left, again, we can see the big inlets, and on the right, we can see that these have now been transformed into that the air actually leaves the room here, right? And then we've got the inlets below this, below the occupants, and then we've got also the stage at the stage, also the inlets, right? So changed approach, same heat, and interestingly enough, also the exact same energy being used, right? So we're bringing in the same amount of air, conditioned the same way. So at least from this conceptual perspective, the same energy is being consumed in this in HVAC design 2. So let's take a look how we're doing now. Again, the approach is the same, right? It's basically the second simulation you saw in my SimScale project, and we can already see that this looks more like what we want, right? We can see we're now bringing in air from here at the stage. We're bringing in air below the occupants, and we can see that the big drafty regions, so the big red ones, have vanished. So they're not there anymore. So it seems like we're moving into the right direction. Looking at temperature, also here, we do not have this, I mean, arguably, it's now very low down here, right, where we're bringing in all the conditioned air. So we still have quite a sort of stratification, quite a gap between the temperature here at the bottom and the temperature here at the top, but it's more homogeneous, right? But still, I mean, that might be one piece of concern, that we're too cold here at the bottom. But the big drafts, again, we can see here the big cold regions in the middle of the occupant region is at least gone. And that's also what's reflected in EDT, right? Effective draft temperature shows that most of our occupants are green. In fact, if you count the number of occupants that are not in the EDT criterion within the bounds of it, it's 0, right? So we seem to have significantly improved the performance, or if you will, the quality of this HVAC system with respect to EDT. The one thing, and now here you can see the difference, because EDT is, or ASHRAE now, also the ASHRAE 55 also looks at temperature, right? So what we're seeing immediately is that while we have removed almost all of these very drafty regions, we're now facing the problem that we're too cold, right? So that's the one thing we probably would need in a third iteration to fix, that we're bringing in differently conditioned air to make sure that the blue regions down here are gone. That's sort of like, okay, we removed the drafts, but the temperature seems to be a bit too low here. Now when comparing these two designs directly with each other, the picture gets very clear, right? Again, on the left, design 1, where we're bringing in conditioned air from the top. On the right, design 2, where we're bringing in conditioned air from below the audience and at the stage. It gets immediately clear, right, that the velocity, we can see these big drafts. I think, it's clear, right? We're seeing chaotic flow happening in the audience. We've got a much more homogeneous airflow in the audience with the right approach. Same thing gets clear when we look at it in a cut section from the side. So we can see here also, we didn't look at this perspective yet, right? So we can see this big vortex that's being formed due to the fact that we're bringing in this air from the top. And on the right, we've got a really, I think, a smooth sort of transport process from the occupant region to the return registers. Same view temperature, right? We can see that on the left, the ugly piece was the blue regions directly below the air inlets. On the right, we've seen already with the ASHRAE 55 plot that the temperature distribution is very homogeneous, and overall, with the same amount of energy being used, we could cool the room more effectively. But the first rows might be a bit too cold, right? That's the one piece that we would still need to fix in a design 3. Unfortunately, we won't do that today, just as a to manage expectations here. Yeah, same view here, right? So we can see that on the left, again, same amount of energy being used. On the left, we can see much harder. On the right, we're using it thermally much more efficiently, but maybe a bit too cold here at the bottom. Exactly. And then EDT, we talked about this as well, right? Here it gets very clear that design 2 is superior, that all of the seats, and again, counting here this number of seats, on the left we've got 15 seats being not comfortable. On the right, we've got 0 seats being not comfortable, according to EDT. That's also, right, what we looked at. We can see this huge plume here. That's not what we want. So that looks good. And then last but not least, the direct comparison here with ASHRAE. So we can see that the problem on the left, so we were hot enough, so that was fine, but the challenge was the draft, right? So a ton of drafty seats. On the right, we can see that we removed all the drafty problems, or most of the draft problems, but we have a temperature problem. So we might condition the air a bit hotter. And the same gets clear in this cut section. Yeah, so to wrap that up, we did see that we basically started with a CAD model. So basically just on rough drawings, you could see that we don't have all details in there, right? So it's really on a conceptual CAD model. We bring in the model, we run a simulation. That takes us, depending on, if a little bit of troubleshooting, maybe a little bit of CAD preparation, a couple of hours in manual time. And then thanks to the access to high performance computing systems, we can cut the computing time significantly down, right? So 20 million cells, or even north of 20 million cells in under 12 hours computing. So that needs a large machine, right? In that case, we ran both simulations on close to 100 cores. So we used roughly 1,200 core hours to complete this. And yeah, ultimately we'll come to a point where we can really assess the quality, or the quality of an HVAC system design just based on the CAD drawings and a very early design system of the building, right? And that helps us to save a ton of money downstream, because the design changes later in the build design process are much more expensive, right? As everyone knows. And in case, I know that many in the audience have already a SimScale account, but in case you do not, it's very easy to get started. So you just go to simscale.com. You can create an account in a minute, and you can give this a try yourself. In fact, the project I showed, this project here is actually a public project. So you can just in our simulation library, so simscale.com/projects, you can find this theater and take a look at the setup yourself and dig into more details if you're interested. And with that, thank you very much. And let's take a look if we have some questions that we can dig into. All right, so it's definitely too many to answer, but to answer all of them. But I would pick maybe 2 or 3 in the time left to keep the session crisp. One participant asks whether or not the ASHRAE 55 results generated, or if they were generated by the software, or have they been done in a post-processing step. And yes, this basically, you cannot directly within SimScale, choose to visualize it that way. So there's a little bit of post-processing necessary, but it's not too complex. And we in fact have small tutorials that explain how to visualize different thermal comfort parameters. Right? I definitely know that we have one for PMV. I also think we've got one for PPD. I'm pretty sure we should have also have a tutorial on ASHRAE 55. And if not, that should be straightforward to do because it's a couple of steps in the post-processing phase. That's correct. Yeah. One registrant asks, what type of model can be used with SimScale? Or what kind of CAD software is compatible with it, right? Fundamentally, how we started is with general exchange formats, right? Such as IGES, STEP, or even STLs you can bring in. And and over time, we've added more and more also commercial formats, right? So nowadays, for example, you can bring in also SolidWorks models or inventor models, so depending on the CAD software. And we're in fact working right now also on compatibility with other AEC CAD systems such as AutoCAD or also Revit. And that will be released shortly. But as of now, so most CAD systems support one of the general exchange formats, such as STEP or IGES, and that works most of the time fine. So that should work. All right, and then maybe one last question, and then afterwards I'll wrap that up. And again, excuse if we can't touch on all questions, but feel free to approach me afterwards via my email address or go to the SimScale forum. Can I create the model in the software itself? Unfortunately, no. So we try to. So SimScale, the philosophy is that the design process of the engineer, of the designer, is not changed, right? So you just work in the CAD software of your choice, and then you bring in a model and set up, and then everything you need from the model to accurate, reliable simulation results shall be provided by SimScale. That's sort of the philosophy there, but you can't model it in there. All right, and with that, I would close today's sessions. Thank you so much for your attention, and take care. Bye-bye.